Everybody. 4.5. Again, this is a bit of a long unit or chapter. I keep breaking them up into smaller units. So we've looked at indefinite intervals and solving those through substitution. And that is where you do not have numbers at the top and bottom here. A definite integral gives you those numbers. So we're going to use substitution to solve this. Again, just like use substitution, we're going to sub this out because I know the derivative of the inside there is 2x, which will help me get rid of this x on the outside. So I'll let u equal x plus 1, du dx is equal to 2x, and then I rewrite it, du over 2 is equal to x dx, and that removes those two things. So the integral then becomes, a bit over here, integral of u cubed du over 2. And then you could do what we did before. So that is going to be u to the 4 over 4, 1/2 there. And that's going to give me u to the 4, over 8. All right. We don't have to put the plus c because when I sub back in what my u was, that's x squared plus 1 to the power of 4 over 8. And it's evaluated from 0 to 1, which is going to give me 1 squared plus 1 to the 4 over 8 minus 0 squared plus 1 to the 4, 8. Which is going to be 2 to the power of 4, which is 16 over 8 minus 1 over 8, which is 15 over 8. Okay, that's one way to do it. It's not wrong. But if it gets a bit long because you're subbing back in, then you're plugging the numbers. When you get to the alternative way is when you get to this point right here, into du over 2, I can use these as my x's and plug them in to solve for u and get new upper and lower bounds. So when x equals 0, u is equal to 0 squared plus 1. The u is equal to 1. What's my lower bound? When x is equal to 1, u is equal to 1 squared plus 1, which is 2. That's my upper bound. And then I can just solve this integral. So that gives me u to the 4 over 8, getting it from there, evaluated from 1 to 2. That's going to be 2 to the 4 over 8 minus 1 to the 4 over 8, which gives me 16 over 8 minus 1 over 8, which is 15 over 8. Same number. Okay, so when you're doing u substitution on a definite integral, you can, and it usually makes your life easier because you're not going back and forth, you can get upper and lower bounds using what you said u was, using your substitution. All right, we'll do one more. Integral from 1 to 5 of x over root 2x plus 1 dx. All right, so what's our substitution going to be? We always try what's in the radical first. X plus 1. So du is equal to 2 dx. So du over 2 is equal to dx. Right. So I've gotten rid of the dx, I've gotten rid of that. I have to get rid of this x, just like we did last night. You rearrange, sorry, last night is when I made the video. You rearrange this to u minus 1 over 2 is equal to x. And that gets subbed in for x. The integral then becomes u minus 1 over 2 over u to the power of a half times du over 2. And we should change the upper and lower bounds. When x is equal to 1, u is equal to, so we're plugging it into there, 3. Should have been 2x minus 1, or whatever. And when x is equal to 5, u is equal to 11. So the bounds change from 2 to 11. All right. So now we're going to solve this integral. Clean this up a bit though, because it's pretty ugly. So integral 3 to 11, u minus 1 over 2 u to the 1 half and du over 2. All right, so we can pull a quarter out. 3 to 11, u minus 1 over u to the 1 half du. The 1 half goes to both. You're going to divide them off. So u divided by u to the 1 half is u to the 1 half minus u to the negative 1 half du. Now we do the integral. So I get 1/4 times u to the 1 half. So add 1 to it. We have u minus u to the power 1 half by half times 2. And that is evaluated from 3 to 11. All right. So 1/4 to 11 to the 3 halves 2 times. That's not very clear right there. Times 11 to the power of 3 halves. 12 by 3 minus 2. 11 to the power of 1 half. Minus, I'm going to plug 3 in. 2 times 3 to the 3 halves over 3 minus 2 times 3 to the 1 half. And this 1/4 is 1 by all that. Speaks in brackets. That's a bunch of algebra that I don't know the answer to. But yeah, some number. I'm going to assume you can do that. I'm not going to do that right now. Okay. And you can just punch that in your calculator. So page 302, numbers 55 to 61, odd, and 65 and 67. All right, so it's just continuation of what we did before, except now we have definite integrals and we're changing the upper and lower bounds. Everything else is the same. All right, so take a break, do that, pause the video, and then come back to me when you're ready. All right, hoping that went well. We are now going to look at even and odd functions. So if you remember, an even function is when f of x is equal to f of negative x. In other words, it has symmetry with the origin. Symmetry with the origin. So for example, if I have y is equal to x squared plus 1. Well, if I want to see if it's an even function, I go, does f of x equal f of negative x? So you just write it out. f of x is x squared plus 1. F of negative x is negative x all squared plus 1. Which gives me, so it is even. And if you see, that is a parabola going up at 1. And you can see it has symmetry across the, did I say origin? That should be the y-axis. Sorry, people. Has symmetry across the y-axis. Whoa. Sorry. Has symmetry across the y-axis. Okay. An odd function is when negative f of x is equal to f of negative x. And that is symmetry with the origin. Okay, so a simple example, if I have f of x is equal to x cubed, I just go, okay, well, is it odd? Well, does negative f of x, negative of our function, equal f of negative x. So this side gives me negative x cubed. This side gives me negative x cubed. So we know it's odd. And if you know the graph of that function, it looks like that. And you can see it has symmetry across the origin. Okay. Also, the sine function is odd. Sine, so y is equal to sine of x. That is odd because there's our sine graph pi. You can see it has symmetry with the origin. Okay, and cosine if you wanted. So sine is odd. Cosine would be an even function because it has symmetry across the y-axis. Okay, so if f of x is even, right? Then there's a couple properties here, and you have an definite integral where the distance on either side of the origin is equal, negative a to positive a, negative 2 to positive 2, etc. And that integral is equal to 2 times the integral from 0 to a of x dx. And the reason you want to put a 0 in is because zeros are easier to handle. It's less work. And if you think about it, let's use the graph that we used before. What it's saying is these two areas are the same. This area is equal to this area. Alright, that's why we can just double it. Go from 0 to here and just do 2 times that. Okay. If f of x is odd, the integral from negative a to a of x dx is equal to 0. And the reason that is, so let's use a cubic. We're actually able to use sine graph. So this is y is equal to sine of x. And this is negative a, positive a. I guess we might as well make those negative pi and pi. but you can visually see that this area, I drew my graph, not great, is equal to this area, right? This area has a value that is negative, so below the x-axis. This has a value that is positive, so if you add those together and since they're equal, you should get 0, okay? So when is this of use to us? An example like this, integral -3 of 3 of some complex polynomial x cubed plus 4x squared minus 3x minus 6. Okay. So whenever you see upper and lower bounds that are the same, think even and odd. Okay. So think even, odd, if upper equals lower bound, because then we can use these two properties here to hopefully simplify ourselves, because we know that we can break this into separate integrals. So I can break this into the odds added together. So it'd be x cubed 2x minus 3 and 3 of 3x dx plus the integral from -3 to 3 4x squared dx plus the integral, or sorry, make that minus the integral of 6 dx -3 to 3. And the reason I did that is because that's an odd function, and that's an odd function, it has a degree 1. If you have equidistant on either side and it's an odd function, like this one here, you know that is 0 and that is 0. Those go away, you don't even have to deal with them. This one, I could separate them like that, or I could write them as 1 4x squared minus 6. That is an even function, okay? From -3 to 3. This is even, it's a parabola opening up. So I can change that to 2 times the integral from 0 to 3 of 4x squared minus 6. So again, making our life a lot simpler. So I can just now integrate this. 4x squared is actually 4x cubed over 3 minus 6x evaluated from 0 to 3. Okay, so I put the 3 in. 3 minus 6 times 3. And then this is why you want to do this. Subtract, you put in the zeros, and everything disappears. On the second half, that's all 0. So really, I'm just evaluating this bit here, which if you do that, you should get 36, if my math is right. So when you see equidistant upper and lower bounds, check to see if the function is even or odd, because you can usually eliminate quite a few things and combine the evens to go from 0 to whatever your upper bound is, and just multiply that answer by 2. All right, page 302, number 69 to 75. Okay, email if you have any questions.